Okay, welcome to the next module on testing. So, this is module number 8. In the last module, what we have seen is that we have understood what is the basic of VLSI testing, why do we require testing. So, the main point of requirement of testing we saw was that as the yield of the VLSI circuits are lower, because we are continuously moving into higher and higher submicron technologies or advanced technologies. So, our accuracy or design means correctness has not yet matured, and then we move to another high end technology. So, always there is chances of failures in the chips or defects in the chips, and our main goal is to eliminate out the faulty chips and then sell out or give to the customers the normal ones. So, and now the yield is lower because of the continuously upliftment in technology. So, what the main aim is that we have to do good testing or somewhat VLSI testing kind of stuff is required, so that we can eliminate out the good chips and discard the faulty chips, and for that testing is an important paradigm in case of circuits. Next we have seen that testing can be functional and structural. So, in functional testing, if there are n inputs, we give 2 to the power n all combinations of input and check against a golden response. So, here our main emphasis is to find that the chip performs fine or the chip performs okay for all the combination of inputs. But as you know that if the number of inputs of a circuit is about 100 or 200, then 2 to the power n is an infeasible number, and testing will take years and it will run into such a huge time that is not feasible. So, we have gone for what you call a structural testing. So, in structural testing what we do, we are not much concerned about the functionality of the circuit, rather we break the circuit into whole circuit. We have seen we break them up into some small modules, and each module we test them functionally, and internal wires you can say that we test structurally. So, in that case we have seen that if your circuit modules or which you are breaking up into sub modules which you are testing functionally, then if your modules are quite large, then what happens is the number of test input combinations are also higher, because the 2 to the power n is also not a very small number if your sub modules are higher. But the advantage that you gain is that the number of intermediate lines between the sub modules are lower, and so testing or controlling and observing these intermediate lines is easier. On the other hand, if you make small modules of your whole circuit, that is, if you have a larger circuit and you have small modules, then number of input patterns per module is very less, that is an advantage, but then the number of intermediary lines in between the modules is very high, and controlling them and observing them remains a challenge, for which you need either pinouts or you require multiplexing arrangements or you require a shift register and so forth. And then we have seen to eliminate out all the problems, we have gone for a structural testing using a fault model. So, what is a fault model? In the structural testing with fault model, we are not concerned at all about any kind of functionality of the circuit. Rather, we want to find out, or whether we want to verify that given a circuit there is no fault from the fault list. That is, we have seen that stacked fault model is one of the well accepted fault model, in case which we have seen that we have given a circuit with AND gates and OR gates, then we have to apply patterns so that you are able to verify that there is no stacked faults at any of the lines. Then we have seen the advantages of stacked fault models is that we do not require intermediate pinouts, we do not require intermediary multiplexers or shift registers to control and observe the lines. Further, the number of one test pattern can detect more than one faults. So, the advantage is that if there are 2n faults in a circuit where n is the number of lines, still 2n number of test patterns are not required, we require much less number of test patterns, because one test pattern can detect a large number of faults. So, there are a lot of advantages when you are going for a structural test with a fault model, and stacked fault model is the well accepted one, and also we have seen that structural testing using stacked fault model is widely accepted, because if you can verify that the circuit does not have any stacked faults, then you can be 99.9% plus sure that the circuit is functionally, or you can say that it can be you can be confident 99.9% accuracy that the circuit is free of defects. So, all those things make actually structural testing with stacked fault model a widely accepted practice or widely accepted model. So, in this module what we are going to see is that how can you generate the test patterns, that is, given a circuit with n number of faults, then after fault collapsing you can reduce the number of faults, then for the remaining fault or whatsoever the case, like for a given circuit and there are different faults which are the final list which has been derived after fault collapsing by dominance and equivalence, then how can you generate test patterns which can detect the fault? That is called test pattern generation. So, in this module or in the module number 8, our main emphasis will be how to get test patterns which can determine or in the other words, how can you find out patterns which can detect the stacked faults which are in your circuit. So, in the first lecture on this is on fault simulation, and it is a quite long lecture. So, you can see we will be spending 3 days, or you can call 3 modules, I mean 3 sub modules 1, 2 and 3 will be on fault simulation. So, let us explore it. So, this is our, so what is the test pattern generation, just I told you. So, given a stuck at fault, if you can, this is a fault say, then automatically you have to find out which pattern can test this fault. So, this is called actually test pattern generation, this is called test pattern generation. And now if the circuit is quite large, then you need to obviously automate it, and therefore it is called automatic test pattern generation, that is called ATPG. So, in this module we are going to look into details on this one. Say for example, this is your circuit, which I also seen in your last lecture. Now, say this is a stuck at one fault. Now, say I want to find out a test pattern which can detect this fault. Okay, so that is my question, that is the main problem of ATPG. So, now you have to also try for fault at this point and fault at this point and so forth. Obviously, the number of faults will be limited by the fault collapsing algorithm. Now, actually this is a 3 process stage. So, you can also find it out as a, I mean what do you call ad hoc, in an ad hoc manner also you can find out. For example, you can say this stuck at 1. So, obviously you have to apply a 0, and then this value should be propagated, this effect, fault effect should be propagated to the AND gate. So, all these should be 1s, and then actually this the fault effect is, you have to apply a 0 normal case, and the stuck at 1, the faulty case it will be 1, and this fault effect has to be propagated at the output. So, all the other inputs of the AND gates are to be 1. Then if all the AND gates output are to be 1, then all the inputs have to be 1 for all the gates, and for this case you have to apply, you have to get a 0 over here. So, either the inputs can be all zeros or it can be 1 0 0 1, accepting 1 1 1 1 all ones, any other pattern can be applied. So, that will be a test pattern generation. That is a test pattern for this fault, that is any other combination other than 1 1 1 1, and all these have to be 1 1s, accepting all 1s at this gate, any other pattern like 0 1 1 1 1 or any other patterns accepting all 1s will test this fault. But there is a proper algorithm we require to do this. This is actually called fault sensitization, propagation and justification. Let us see what it does. So, first is called the, again just like our heuristic we have discussed the same thing. So, the first is called fault sensitization. So, what do you mean by fault sensitization? We say that the output net of G1 is stuck at 1, we need it to drive it to 0 to verify the presence or absence of a fault. So, just you can take the analogy of a say electric bulb which is fuse, which is, so now if you want to test it, you have to make the switch on. So, if you switch the bulb on, then if it is fuse, then the bulb will not glow. That means what? In that case you are sensitizing the fuse fault. The bulb is fused, so it is a fault you are sensitizing. So, in this case they are saying that you are sensitizing it. So, sensitizing means if it is a stuck at 1, so you have to apply the reverse value. So, I have to apply a 1 over here. So, that is actually called the sensitization. Now, next step is actually called the fault propagation. Now, as already discussed in the last chapter, or I mean last lecture, that for structural testing with fault models, you do not need to bring out any extra pins, neither you require any kind of a multiplexer arrangement, neither you require what you call a shift register kind of a thing. That is, if you have a circuit and then you have a lot of gates inside and you are going for structural, these are the primary outputs and these are the primary inputs, then we do not require any kind of extra pin outs or extra what you call this shift register to control these, like these things are not required. So, in structural testing with structural fault model, structural testing with fault model, so what is our idea is that whatever you have to do it from the primary inputs and the primary output. That is why what you have to do, this fault effect. So, what we are seeing, this fault effect, the fault effect is what in the normal case, sorry, this is a stuck at 1, so you have to apply a 0, I am sorry. So, the effect is this one, which is actually 0 in case of fault and sorry, normal fault 0 and fault is 1. This effect has to be propagated to this output. So, because whatever you do, you only do at this output, we cannot have this pin out, this pin out is not allowed. No pin out is, in fact, extra pin out is allowed. So, you have to bring this out. So, now in the output also effect will be this one. So, it is already written 1 if fault and 0 if no fault. Now, this is actually called the fault propagation. Now, the fault is propagated. Now, you have to justify that. What do you mean by justification? Just mean determination of values at primary input, so that fault sensitization and fault propagation are successful. Let us see what does it mean. So, again as I told you, you do not have any multiplexer arrangement here, you do not have any multiplexer arrangement here, you do not have any multiplexer arrangement here. So, indirectly what is happening? You cannot control these lines. Okay, so I mean to have this fault value propagated from this point to this point, you cannot go for any additional control here. So, whatever control you have to do at these lines and these lines, you have to do only from the primary input. So, structural testing with fault model is nothing but controlling through the primary inputs and observing through the primary outputs. So, now you have to sensitize, propagate, you justify. So, you have to justify that this effect or all this input and this input is by controlling the primary inputs, you have to justify that these things are successful. So, it is an AND gate. So, just go from one level. So, next level is that this effect has to be propagated to this one. So, if this effect has to be propagated, all the other inputs of this AND gate has to be 1. So, this is the level 1 justification. So, this is level 1 justification, right. Now, again now what happens? So, again then now level 2 justification is saying that output of this gate is 1, output of this gate is 1 and the output of this gate is 1. So, how can you get this justification of the second level to be 1s? All input of a AND gate has to be 1. Similarly, for all this has to be 1. Now, remains this one. So, in this case you require a value of 0. So, this has to be justified at the level 2. So, again justification AND gate output to be 0 is all pattern or any pattern excepting all ones. So, your ATPG algorithm will generate 0 1 1 1, it can also generate 0 0 0 0 0, any one of them, that is arbitrary and that depends on the some level of heuristics or some accuracy that we will see in the, when we will be dealing in details on ATPG, we will see it will determine whether you will generate 0 1 1 1 or all zeros or 0 0 0 0 1, it depends on many other factors. But for the time being, the ATPG generation algorithm will justify this 0 by any pattern which is 0 1 1 1 0 0 anything. So, in this case let us assume that this is the pattern, that is 0 1 1 1 has been generated, and for justification of 1 1 in this case you get 1 1 1 1 1 1 1 1. So, the test pattern generated is 0 1 1 1 and all other inputs are 1 1. So, it tests are stuck at 0 fault, sorry, are stuck at 1 fault here. So, this is the basic steps of fault sensitization, propagation and justification. So, this, so for all the faults if you do this, you are going to get what you call the or test pattern generated for all the faults. Now, when all the test patterns are generated, they are stored in the memory. So, when this IC is fabricated and it comes from the what you call fabrication unit, so each IC you have to apply those inputs and you have to verify whether none of the faults, target faults would be present. So, if you apply all the test patterns, so automatically you will find out that if none of the test patterns is giving a otherwise result, that is if all the test patterns are verifying that there is no fault, so you can say that your circuit is free of stuck at faults and it can be shipped to the market. So, as already told you, so the test pattern generation procedure would generate any pattern in the table 1. So, it can generate all zeros with all 1. So, this can be 1 1 1, it can be 1 1 0. So, 2 to the power 25 minus 1 test patterns can be possible for this target fault, and it depends on the ATPG algorithm whether we will generate 0 0 0 0 for the first AND gate or 0 0 0 1 for this one or 0 1 1 1 1 1 for the first gate. So, it depends, but anything would do your job because we require 0 at the output of the first gate and all ones and ones at the output of all the other AND gates, right. Now, the question arises that do we require to do this individually for all faults. So, now what our goal in the last module we have seen that our goal is to reduce the test generation time or the test application time. So, you have to go down in time. So, from 2 to the power n input patterns we came to k, where k is the number of stuck at faults, that is 2n. So, if there is n lines, so there are 2n number of test stuck at 0 faults can be possible, and if there are 2k number of if there are n number of lines, then 2n number of stuck at faults can be possible. So, k patterns that may, for each stuck at fault, if you assume in the worst case is one pattern required. So, k pattern, that is 2n patterns is required in the maximum case. But again you can see that by structural fault collapsing by dominance and equivalence, you find that it is much less than even k. So, it is k by a factor, k is also much reduced than k. So, even if there are n lines in the circuit, number of test pattern stuck at faults are much less than 2n because of the collapsing, and so test pattern requirements are even much less than that. So, now again we are going another level down, so that even if we have some say p number of faults after all the fault collapsing, so we require at least p number of test patterns to detect it, because 2n is the number of faults, or for 2n is the number of, if n is the number of nets in the circuit, so at max we have 2n stuck at fault, stuck at 0 and stuck at 1 for each line. By collapsing we have reduced it to p. Now, can we go even less than p? Can we have any number of, can we declare, say that the number of test pattern requests are even less than p? The answer is yes, because sometimes you may find out that one test pattern can detect more than one number of faults. That also can be possible. So, that is actually called what do you call single pattern can detect multiple number of faults. So, therefore, if you are repeating, if you are taking the approach of sensitize, propagate and justify, so what you are doing, you first take one fault, then you do a sensitize, propagate and justify and generate one pattern, say P1 you are generating for this one. Now, you take another pattern, do a sensitization, propagation and justification done, you get pattern P2. Similarly, you keep on doing this, and after that you say get PL, is the number of fault, th number of fault you do, and you generate say PL, sorry, PL is the pattern. What I was saying, that you have fault P1, then you have fault P2, then you have fault PL. So, for that you are generating say PP1, this pattern 1, then for fault number 2 you are generating pattern number 2, and here you are generating pattern number K for fault PLK. But now you find out that PL1, that is for fault P1, if the pattern you are saying PPL1 is equal to PPL or PL, that is for the nth number of fault and the first number of fault, the same pattern is generated by this automatic test pattern generation, that is sensitized, propagate and justify. So, you are at a loss, because the same pattern, that is at PPA1 or the pattern for the first fault you have generated, that is what is happening is that that same pattern is detecting more number of fault, that is the first pattern is detecting fault number 1 as well fault number L. So, unnecessarily we are wasting time in automatic test pattern generation using sensitize, propagate and justify, where the same pattern can detect multiple number of faults. So, let us try to think it in some other way. Can I do something so that we apply one pattern and find out how many faults are detected, and then remove those faults, and then try to apply another pattern and see how many faults are detected and so forth. So, in this case what we will save? We will save the unnecessary load of the case where one pattern can detect multiple number of faults. Like in this case, pattern number 1 is detecting 1 as well as pattern the fault number L. So, there is a redundancy. But if you have say that if I apply say pattern PP1 and then you find out which faults are detected, then automatically you will be able to tell that it detects fault P1 and also detects fault P2, sorry PL. So, in this case you will be saved from executing the same algorithm twice for fault number 1 and fault number L. So, we will see that. So, that is actually called fault detection by random random pattern generation. So, in this case sensitize, propagation and justify by this approach, when you are going for test pattern generation, it is called a deterministic approach. In this case you are sensitizing the fault, propagating the effect, and you are justifying this. And when you are doing it randomly, you apply a pattern and then see how many faults are detected and again repeat this, then we call this a random pattern generation. So, we will see that. So, both of them have their own advantage, slowly we will see, but as of now it appears that which is more advantageous? The more advantageous is the random pattern generation. You apply a pattern and see how many faults are detected. Let us consider the same circuit. If you consider back, we will take the same circuit here, the same circuit we are going to consider. This is the same circuit we are going to consider, and now say what can you do? Say some faults are there, some stacked faults and stacked 0 faults are over there. So, now what do you do? So, you say randomly you apply this pattern. Just all of us sometime you dream that this is a very good pattern, you apply. Then you can find out that what are the faults that are detected. So, you can find out that more than one faults will be detected by this pattern. So, 0 0 0 1 1 1 1 1. So, this pattern, let us see what happens. So, in this case you are applying all ones, and here you are applying say 1 0 0 0 1, some pattern you are applying. So, which faults are detected? Obviously, this is 1 1. So, this is 0 over here, this is 1 1 and this is something. So, okay. So, obviously, a stacked 1 fault is detected over here. Yeah. So, obviously, a stacked 1 fault will be detected by this, because all lines are 1 and you apply the pattern 0 0 0 0 1. So, it is 0, and so obviously, a stacked 1 fault is there. Similarly, the same thing you can also say that it is also detecting a stacked what you can say is also detecting is a 0 over here. So, obviously, it is also detecting a stacked 1 fault over here, because in this case the answer is 0, but if a stacked 1 fault, so the answer will be this one. So, similarly, you can see that one random pattern is detecting this 2 faults. Okay. So, we can also have more examples of similar nature. So, in this case, now if you see that I apply this pattern. So, in this case it is detecting 2 faults, stacked 1 at the net of this one and stacked 1 at the net of this one. Okay, 2 faults detected. Now, so the next random pattern is this one, all ones. So, all ones, which one is going to happen? So, if you are applying all ones over here, all ones, then obviously stacked 0 fault at any point of the circuit is detected. That is, stacked 0 of here will be detected, a stacked 0 will be here detected, a stacked 0 here will be detected, and so forth. But if you are going for, now if you take the example, let me just elaborate on this part. So, by fault collapsing and all those things, so we have seen that generally we are going to have a stacked 0 at one input of the AND gate, and all stacked 1s will be there, all stacked 1s will be there, right. So, in this case also one stacked 0 will be there for one input, and stacked 1 at all the input lines will be there. all AND gate inputs have and only one will have a stuck at 0 fault by equivalent. Now the random pattern generator is all ones. So you can easily find out that if you are applying all ones, then what can happen is that the same pattern will detect a stuck at 0 fault here, and it can also detect a stuck at 0 fault here, and also it can detect a stuck at 0 fault here. So one random pattern can detect stuck at 0 faults at all lines in the circuit, and if you consider fault collapsing, we will not have stuck at 0 faults at all the lines of the circuit, but we will have one stuck at faults at each input, each AND gate input. So if there are 5 AND gates, so you will be able to detect 5 stuck at 0 faults by the same pattern. So random, but if you are using the sensitize, propagate and justify approach, then for the 5 stuck at faults at this point say, at this point say, and this point say, so what you have to do? You have to first apply a 1 over here, like for example, if you take this approach, so it is a not a simple one. So if you have stuck at 0 fault over here, so you have to apply a 1 over here, then you have to propagate this value to be here. So you want to propagate the value here, so all other will have to be 1. Then sorry, you have to propagate the value here, so it will be in case of normal 1, fault in case 0, and then again the effect has to be propagated from here, because we are testing the stack at 0 fault here. So 1 you have to apply, this is the normal 1 fault 0, normal 1 fault 0. Now you have to this is the propagation, now you have to justify. So these lines has to be 1, right, and then if these lines has to be, all others has to be 1, all others has to be 1, and here also everything has to be 1 if you want to apply. So again you have to repeat the same thing for a stuck at 0 fault here and stuck at 0 fault. So it's a long procedure. Okay, so if it's a long procedure, that is the problem. But now by random pattern generation, it is very simple. You apply this pattern and you can find out that we can detect a much more larger number of faults. In this case, you can see 33 number of patterns faults has been detected by this approach. So as of now, it seems that this is a very good idea that you go for a random pattern generation based testing rather than go for sensitize, propagate and justify. So what is the idea of, let us look at it. So what is the basic algorithm? You check a random pattern, any random pattern, then you determine the output of the circuit in the random pattern. In the normal circuit, don't consider any fault, but determine the output of the circuit for that random pattern. Now take one fault from the fault list and modify the circuit. Okay. So for example, if the stuck at 1 fault at the output of G1, if you take, say for example, the same circuit. So in this case, if you are taking a stuck at 1 fault here, okay, so the output of this AND gate functionality will be output of G2 and output of G3 dot 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 output of G5. Because this is stuck at 1, so this gate input has no effect. So the Boolean function will be modified as O of G2 and O of G3 and O of G4 and G5, because this is modified because it is already stuck at 1. So this has no controllable effect on the AND gate. So just modify it. So it is 1 that is already there, and of I2, I3, I4 and N5, which is equivalent to this one. 1 is removed. So Boolean function is modified. Now you determine the output of the circuit, that is change circuit, the circuit with the fault for the random pattern, for the same random pattern as input. If the output of the normal circuit varies from the one with the fault, then the random pattern detects the circuit under consideration. So what we have done, we have taken the circuit, we have applied a random pattern and we have recorded the output. Now what we do, now we change the circuit with the fault, now apply the same random pattern, and if we find that the output varies, then that pattern, random pattern detect that fault. Now we next what we do, we again we delete the fault and say that it is detected, then we take another fault and find out what is the case, whether the same random pattern detects another fault or not. So the steps are detected for the other fault in the list, this considered till all the faults are listed. Right, this is how it is, the random pattern goes. And you can easily see that random pattern approach is very easy, just you have to apply the pattern and just you have to find out the output of the circuit. It does not require any kind of sensitization. And one thing I should point out, which we will be discussing in details in the future lectures, that always sensitize, propagate and justify approach may not be successful. That is, you may be able to sensitize a fault, propagate the value to the output, but you may not be able to justify it. Then again you have to reiterate and find out another way of propagating the fault output. Maybe there are multiple paths to propagate the fault to the output. Say for example, if there is an AND gate over here and the fault can be propagated through here, the fault can be propagated through here, the fault can be propagated through here. So you may try out with this one. Then what may happen is that you may find out that you may not be able to justify it, or you may not be able to propagate it through this. Then you have to try through this part and you have to try through this part. In other words, there can be requirement of lot of backtracks if you are going by the sensitize, propagate and justify approach. So in that way, the random pattern generation is very much efficient algorithm, in which what case in what we do is that we apply the test pattern, find out the output of the circuit, and then we modify the circuit with the fault and see if there is any difference. That is a very simple idea. Now the question is then, do you require the sensitize, propagate and justify approach? The answer is yes. So, statistically this graph has been found. So, what is they are saying that if the circuit has say 100 faults, then what you do, you apply the first random pattern, then it detects 20 number of faults. Next random pattern you do, it says they generate another 20 number of faults. This keep on goes and then it saturates. That means what, up to around 90% of the faults you can get a very good fault coverage per random test pattern. That means what, you apply one pattern, it detects 10 faults. You apply another random pattern, you get another 10 faults. Then you apply another random pattern, you get 8. If you keep on doing it, after that there is some faults which are called difficult to test fault. By applying random patterns, you may not be able to test this fault, or in other words, you apply 10 random patterns, you detect 90 faults. For the rest 10 faults which we are calling a difficult to test fault, you have to apply say more than 30 number of random patterns. That is, first random pattern you apply, after 90 no fault is detected. You apply another random pattern, none of the 10 faults are detected. You keep on doing it, say after 31st random pattern, say the fault, one of the faults get detected, and you keep on doing it. So, you have to apply a great number of random patterns to detect those last 10 number of faults. So, whenever you find that the number of random patterns are getting a saturation, or you are saying that it gets saturated, that is the efficiency of random test pattern generation gets satisfied, saturated. So, after say 90% of the faults, for the rest 10% of the faults, you find out that after applying 10 random patterns, one fault is getting detected. So, after that it is actually become more difficult than the sensitize, propagate and justify approach. Then what we do, after that we stop random pattern generation approach. That is when we find that 3 consecutive random patterns or 4 consecutive random patterns are not able to detect any new fault. Then what we do, we stop at that point, and from this point we term them as difficult to test faults, and for them what we do, we apply sensitize, propagate and justify approach of doing it. So, you cannot say that sensitize, propagate and justify approach is a very very difficult approach, so you should throw away with it and we should always go for what you call random pattern generation. This is not the case. For the first few faults, or for 90% of the faults, random pattern is very good, because you can detect large number of faults by the just applying a random pattern and verifying which faults are getting detected. But once you get a saturation, after that the random pattern generation becomes inefficient, because for one pattern you may not be able to detect anything and you have to keep on doing it till you get a fault. So, for those faults it is better to go for sensitize, propagate and justify. So, we can give a very simple analogy. So, I think all of you might have gone to fairs or melas where you have a balloons. So, where there is a board where there are a lot of balloons over there and you have to shoot with a gun. So, what you can do, if there are a lot of balloons in the board, then you can randomly shoot and some of the balloons get busted. That is true. Even if I do not have a very good aim, so what I can do is that I can randomly fire the bullets and most of the balloons get blasted, or at least few of the balloons get blasted. Now, why it happens? Because there is more number of solutions or more number of points, and randomly firing gets an answer. The same thing happens here. More number of faults are there, so you can just apply random patterns and you can detect the fault. But when the number of balloons remains very less, that most of the balloons you have blasted and a few, say around 5 or 6 balloons are remaining. So, at the time what happens? At that time it is very difficult, then you have to aim and then find out how far is that, how low, how you are holding your gun, and all those precautions you have to take care, and then only you can blast the balloon. So, it is same analogy here. So, when lot of faults are there, you can randomly do all the thing, but whenever the number of faults are coming to be less, then what you have to do? Then you have to go for a very aimed approach, which is called the sensitize, propagate and justify. So, same analogy here. So, in the first we will go, so actually the test pattern generation is done in 2 phases. First we go for a random pattern, whenever a random new pattern detects a reasonable number of new faults. When you find that is not being done, then we go for a sensitize, propagate and justify approach of detecting the faults. So, this is actually the second phase, so which we will be dealing later in the part of the course, but now we will see how we can efficiently do this. So, for we have seen that for circuit test pattern generation by random pattern. So, what we have to do? We have to take the circuit and give some input and get the output. So, that means what? There is the circuit is there, but you have to know the circuit is not yet fabricated. So, we are finding out which patterns have to be applied when the circuit is fabricated. So, all this test generation activity is being done when the circuit is being designed. Fabrication has not been done. So, we do not have the circuit in the hard form, that is, we do not have the fabricated version of the circuit. So, we have say the circuit in soft copy, say in a program or some other manner, this is soft copy. So, only soft copy is available, and then you have to find out which patterns. So, by random pattern, so you are applying some random pattern 1s and 0s, so you have to find out the output. So, that means what? You have to simulate your circuit. So, what do you mean by simulation of the circuit? The imitative representation of the functioning of the circuit by means of another alternative, say a computer program, is called simulation. That is, you do not have the hard copy of your circuit, or you do not have the hard version of your circuit or the fabricated circuit, you do not have. You apply some patterns and this circuit is represented in a computer program and you can generate the output. After that you can apply the fault and repeat the same thing. So, in other words, you do not have the hard copy, but you represent the circuit in a computer program. That is very much required for fault test pattern generation by sensitize, propagate and justify approach. So, we will study in detail circuit simulation and also about fault simulation. So, what do you mean by fault simulation? In fault simulation, the circuit is there as a program and then a fault is inserted in the circuit which is represented as a program, and you find out what is the output corresponding to a random input. So, first we will see something called a compiled code simulation. So, what is a compiled code simulation? The whole circuit is represented as a C program or any other program, and you generate the output for input based on the C program. Just like compiled code simulation involves describe the circuit in some language which can be compiled in a computer, like it can be hardware language by Verilog, VHDL, or it can be simple C, and then you have to give some input and you get the output, and you can repeat it as long as you want. Say for example, a very simple circuit, 4 inputs and 1 output. Now, how do you do this? So, you can represent it in C. So, you have lines like 1, 2, 3, 4, these are the input lines and these are the output lines, these are temporary variables. Now, you printf, input the values of this one, then you scanf, then you do this, do ANDing and then final ANDing, and the output of the circuit is so. So, different inputs you can give and different outputs you can get from the circuit. So, this is a very simple approach. Now, if you want to find out some fault, maybe some stuck at 1 fault is there or some stuck at 0 fault is there, you can if some stuck at fault is there for AND 2, then this can be ANDed with 0 and so forth. Just you can modify the circuit for the different kind of a fault, and then you get the compiled code fault simulation. That is very simple. Just you have to apply a what you call fault for doing it. But now you see what happens. Say for example, you give input as 1 1 1 1 and then you generate the output. So, what will happen? So, if you give 1 1 1 1, so first what will happen? First this sentence is executed. So, it is 1 and 1. So, OG 1 is equal to 1. Now, then these things are also 1 1, then OG 2 is also computed to be 1, and then this is done, then O is generated to be 1. So, it is a 3-step computation. So, fine, this is done. Next what you do is that, say next you apply 0 1 1 1, that is the next random pattern. So, in C language what is going to happen? So, again the same code will run and it will take 3 steps. So, it will be 0 and 1, that is equal to 0, this is 1. And this is 0 and 1 is equal to 0. So, answer is 0, but it again takes a 3 step. But if you clearly observe this circuit, we do not require to do so much activity, but because you see this we are changing from 0 to 1, fine, this is no change, this is no change, this is no change. So, output here is changing from 1 to 0 and this one is changing to 0. So, only 1 bit, 2 bit computation or 2 line computation is fine, that is you need to compute this obviously, this you need not compute. Because already it is same, obviously you need to compute this and do it. So, that is what this circuit, there are some changes, but if you are going for a compiled code simulation, then the problem is that you have to have a simulation for the entire part of the circuit. In other words, now you consider it as a very big circuit and you say that there is no changes in other parts of the circuit and only a minor change here which is reflected only part, minor change. But now, if you are going for a compiled code simulation, then what will happen is that the whole circuit will have to be resimulated, and which is actually going to give you a big problem. That is, unnecessarily just for a minor change, your whole circuit you are going to go for a compiling changes, then you are executing, everything is re-evaluated. So, even if a very small part of the circuit is being changed, but for the compiled code simulation, then you are changing or you are recomputing or you are doing redundant computation for other parts of the circuit. So, to avoid this one, we call event driven simulation. So, what is the idea of an event driven simulation? So, the idea of an event driven simulation is something like this. Say for the same circuit we take, so for the same circuit if you take, in case of event driven simulation, what is happening is, so this is the event, okay, and there is no event in this part of the circuit, maybe some other big circuit is there, there is also no event. So, this part will not go for any kind of a computation. So, what we will do, only we will go for computation of this part of the circuit where there are some event changes. So, that is actually called event driven, these are some of the events happening. So, this is actually called event driven simulation. So, it will save lot of time in your computer execution of the fault test pattern generation by random pattern. So, event driven is very efficient because it detects any signal changes and that triggers other signals. So, it is done in a recursive manner, we will see with an example how it is done. So, for example, the same circuit we take, so this is a first change. So, time t equal to 0, so one change is this one, I equal to 1, so this change is 0. So, now only the next level test patterns or next level signals from this gate, because this is re-evaluated, will come in the activity list. So, only OG1 will be in his activity list. Now, why is that so? This will be because the output of this gate is only OG1 and only one level jump is allowed, one level jump, only one level is allowed. So, this is a change here. So, only this can be in the activity list. Okay, then fine. So, you re-evaluate this is the case. So, OG1 changes from 0 to 1. So, OG1 changes from this one. So, only the activity list will be output of this one, because only one level is allowed. So, this change is there. So, this will come in the activity list. This one is the case, and then this evaluates to be O equal to 0 and nothing in the activity list, and you stop. So, you just require a very small number of computations to do it, and you do not do any kind of a no computation required. No computation is required for this, only you require this. So, what is the basic idea here? You have a circuit and you have some gates. So, basic philosophy of this one let me discuss. So, what we do is, we have something like, we have a gate like this, some signal change, some signal change is there, then output of this one will be in the activity list, that is it. And again any change here will be again corresponding to this activity change. For example, if you have something like this, say this had been the case, say for example. Now, in this case what would happen? Say this was our initial pattern was 1 0 1 1. Now, you change this one from this one. Now, what will happen? I equal to 1 to 0, activity list is O equal to 1. Now, activity 0 1 and a 0 and a 0, the activity list is 0. So, initially it was also 0, now it is also 0. So, the activity list will be empty in this case, because it is 0 to 0. So, no change is there and everything will stop over here, and this change is also not there. So, in level 2 the propagation will stop. But if you are taking a compiled code simulation, then you have to evaluate this, evaluate this, evaluate this and so forth, and it is a wastage of time in computation. So, event driven simulation is helping a lot. Now, we have to go for circuit simulation. So, what do you mean by a circuit simulation? In case of a we have seen about circuit simulation. Circuit simulation means what? A circuit is there and then you are applying some inputs and you are finding out the output, be it compiled code simulation or event driven simulation. But for a fault simulation, but we know that for random test pattern generation, what you have to do, you have to put the fault in the circuit and then you have to go for fault simulation, circuit simulation. So, for fault simulation is nothing but if you have a circuit with a fault and then you have to simulate the circuit for the some output for some given input, you just find out the output, it is called fault simulation. You can also call fault circuit simulation also you can call. You can also call it fault circuit simulation. So, fault simulation is like an ordinary simulation, but it has two versions, one is without fault and one is with fault. That is a very simple idea. So, if the output of the faulty circuit is not matching with the output of the normal circuit, that is what is desired, then you know that the random pattern or the pattern is detecting the fault. That is what is the idea of fault simulation. Let us see, this is a block diagram which shows this. So, there is some random pattern. Now, what happens? So, you are applying what you called this circuit with fault 1, fault 2, fault 10, all the faults are there and this is normal circuit output. You are comparing this one and then if there is a mismatch, this fault is detected, this fault is detected and you remove them and you take random pattern number 2. This is how it is done. So, we have if you are how we are improving it? You are improving it using what you call the event driven simulation. So, if you are using event driven simulation, so you are simulating circuit 1, circuit 2, circuit 3 with faults and this you are also with fault 1, fault 2, fault 3. So, even if you are doing it with fault, so there can be little amount of changes in the whole circuit. So, even if you are doing a what you call the event driven simulation, so you can save a lot on the computations. So, that is one way you are saving, but only another factor you are saving we are not doing. Another thing is that in one random pattern we are trying to see if one fault is detected. So, there also we can parallelize. So, two way of making it efficient, one is event driven which is already seen, and that is parallel. That is, here what we are doing, we are taking a circuit, applying one test pattern, random pattern and see if the fault is detected, then with fault 2 and fault 3 and so on. So, we need to also think if we can find out that given a random pattern, how many faults it can detect in one go. That is one good way of doing it, and that is event driven, because if you are going for compiled code simulation, then even for a small number of fault change or the input pattern change, you have to go for a full code simulation. So, that is one thing these are two factors we have to improve. So, one improvement is this event driven and that is parallelism. So, both of them we are going to see in details. So, but if you are not doing anything for this even random pattern generation, random test pattern generation is also not very simple, because the time is how much number of faults for the ith random pattern. Say for the ith random pattern, still say for example, we start with 100 faults. First pattern, for the first pattern, how many faults we require to check for? All hundreds we require to check in pattern number 1. Because 100 faults are there, you have to check for 100. Say for 10 patterns, 10 faults get detected by the pattern. Very good. Now pattern number 2 comes, then again 90 remaining faults has to be tested for that. Say 20 faults get detected some by some reason. Then for pattern number 3, you have to go for 70. So similarly, you go and say for the 10th number fault, there is only 10 patterns remaining, and say somehow only 1 fault get detected. Then for the 11th pattern, 9 faults has to be checked. 12, 9 fault, because this is saturates. Say up to 100 patterns, 9 faults has to be tested. Generally we stop at this point because things have get saturated. But you see, for the first pattern 100 faults has to be checked for fault pattern 2, 90 faults has to be checked for, and so on. So I mean, if you do not have a parallel fault simulator, that is, I mean, if you can somehow parallelize the algorithm, that is for a single pattern you can check whether among these 90 faults, 100 faults are there, can you check parallelly that whether all the faults are detectable by this random pattern, would be a very good idea. And also apart from that, also you should be able to you should be able to simulate your circuit for minimum requirement. Only those things are changed, that only you should be taking into picture and not more. So we say that the number of, that is event driven simulation. So whatever minimal changes is there, only that part has to be resimulated and other things are to be retained. Again, you should avoid you should avoid redundant simulation. We say that the time for fault simulation is faults for the highest random test pattern into simulation time, that is fault simulation normal value is always there, and number of random patterns you are going for that. That is not a very small number. Okay, so we have to see. So that is what is improving fault simulation algorithm, that is minimum computation change, that is event driven simulation. So whenever there is a pattern change or whenever there is a fault change, minimum changes are there, then you have to go for only incremental simulation, that is event driven simulation. You should not simulate the whole circuit, and determine more than one fault can be detected by a random pattern, that is check is parallelized. So if these two features we can build in, then our things will be improved. So that is what we are going to do. So first we are going to see a very simple fault simulation algorithm, which is called the serial fault simulation. That is the very simplest one. So in this case what it is done, so it is nothing but you apply a pattern, then you apply one fault, the serial, because serially you are going to check, then you see whether you apply a pattern, then apply a pattern, then take one fault and see if the fault is detected by the pattern. If so, the fault is dropped, and that is fault is considered and is already been tested. Then you take another fault, see whether it is detected by the same random pattern, and so on. One by one you test for all the faults which is remaining, and then when all the faults have been checked for, say you get that n number of faults has been detected. So that you remove from the circuit, that out of 100 some 10 faults have been removed. So now for the 90 faults you repeat the same procedure for the next pattern. So that is the next fault are introduced one by one. That is a very important thing here. This one by one you are introducing the faults and doing the fault simulation. So if the output is different, faults are detected and so forth. But for the simple serial pattern, so that is the very important. I mean, that is the main idea, is that one by one you are taking. But again, one thing we have to remember, that always we are going to use event driven simulation, and even then we are going to improve on serial, parallel, deductive and all those things. Slowly they will come into picture. So let us study serial fault simulation with example. So let this be the circuit. This circuit you can see. So one thing I should say here, that this is input I1 G. So this is, all fan outs are different if you remember. So this is I2 G1, this is I2 G2, this is input 2 of G2, some names we have given. So this output is O2, this is O1. So in testing, as you know, all fan outs are different. So I am putting a different name to this one. Also it is I1 G3, so input 1 G3, this is output G2, no problem. So this is the one. This is, I should remember, I1 G3, sorry, I1 G3, this is this net. Okay. So now, so there is a stuck at 0 fault over here. So what you have to do, say for example we do a random pattern is say 1 1. So what is the output of this circuit? Normal case O2 equal to 1, O1 equal to 0. That is very simple, because 1 1, so the answer is 1, so it is 1, and in this case it is 1, it is 0, so the answer is 0. So 1 0 is the result for the normal circuit, and this is the random pattern. Right. So now we are going for this one. So, the same random pattern, and we are going to see whether this stacked fault is detectable or not. So, this is serial, so we will take one fault at a time. So, this is one and a one event driven simulation. So, as I already told you that only one level is allowed. So, this is in the activity list and this is in the activity list. So, only two things will be in the activity list. So, what you have here is I1 equal to 1 and I2 equal to 1. Sorry, and this one will also be there because this is also in the list. So, activity is I2G1 is the single level, OG1 same level, and I2G2, this is I2G2, because this is the signals we have and this is the one level change from the signals. So, one level change from these things. So, you are going to have these things as the activity list, because you are saying that these signal changes, that is input equal to 1 and input equal to 1, these two equal to 1 1 are going to have direct impact on these 3 points only. This one is a direct impact. So, these are in the activity list. Now, if you have this 1 and a 1 over here, so you can compute this to be 0 because of the stacked fault, this is 0. So, I1 G1 is 0, and then this is also I2 G2 is also 0. This you can compute, but this you cannot compute because in the second round this value is not known. Sorry. Okay. So, what is in the new activity list? This one is in the new activity list because of this, and this one remains in the activity list. This could not be computed because in the first value this one was not known to us. Correct. So, now in the next activity list, we have OG1 and OG2. Now, what happens? Now, what we do is that, so now we have the values over here. So, we have OG1 equal to 0, this one we know OG1 equal to 0 and O2G1 equal to 1, these things we know. Now, what is in the activity list? The activity list will be now O1, because of this one we have O1, because this value is known. So, this point is also known, which I call I1 G3, this is I1 G3, okay, and O2. Obviously, this one will be there because this is there. So, one value jump will be there. This one level jump is allowed. So, this is your thing. Now, you can easily see that if this one is a 0, so next jump O2 is equal to a 0. And if you look at the normal circuit, O1 was a 1. So, you can stop at this point, say that 1 1 detects this stuck at 0 fault, because in the stuck at 0 fault this is 0 and normal case it is a 1. So, it detects the fault. And the thing is that, so this is by a random pattern simulation. So, I mean this we are doing event wise, because we are doing only for those parts where there is a signal change. Now, so one fault has been detected. Now, let us see what next. Same pattern is there, we are going for a serial fault simulation. So, we are going for this fault. Okay, another fault we have taken. These are stuck at one fault over here. So, this one has already till I1 G3. This is there for you. Okay. So, now again we are going to look at for all these things. So, now what happens? So, this 1 1 say a random pattern. So, now in this case this 1 1. So, activity list are these 3, this point and this point. So, this is the value. So, now you are going to get 1 1 over here, because the fault is here, not here this time. So, you are going to get I1 and this one. So, these values are there. So, if these values are there, so we are having OG1 as this activity value, already it was there, it will be computed, new one added is OG2. Now, you see, so this is 1, and in normal case the output should be 0, but as it stuck at 1, OG2 will be 1, it is not 0 because of the stuck at fault, and OG3, if you see I1 G3 is 1 because this value is propagated. So, these values you get, okay, and sorry, this is the pattern which I was saying. So, OG1 and OG2 you get. So, OG1 is 1 and OG2 is also 1 because of the stuck at fault over here. The activity list in this case is output 1 because this value we have, and then I1 G3 because of this value, this is also in the activity list, and obviously O2 will be in the activity list. Now, what you do? Now, new value which we are obtaining out here is O2. So, this O2 is equal to 1 because initially we have it, now we are having a value of 1 over here. So, O2 is equal to 1, and as well as we are also having this value from here to here it is 1, as well as from here to here it is 1. So, I1 G3 1, that is this fan out is also having the value of 1, and in the activity list is now 1 because this signal is ready. Okay. So, it was also there, but initially we could not compute the value because this value was not ready, value of this fan out was not ready. So, in the what you can call in the second step the value was not ready. So, we could not compute it, but now in the third step this value of O1 is ready. So, in the value of step number 3 this value is also there, this value is there. So, we can compute O1. So, now this is in the activity list, and the fourth stage O1 equal to 1. So, if the fault is captured because in the normal case the answer was 1 and this answer was 0. So, fault is detected. But there is one difference you have to observe here very carefully here, that here we require 4 steps to do it, and here we require only 3 steps to do. So, that is the beauty of compiled code simulation. So, we are going event wise, whenever we detect that there is a difference with the normal circuit, we immediately stop. So, for this fault we did not go for computation of this one, which required 4 steps. So, we could have easily stopped at the 3rd stage, and we find out that the answer is there is fault simulated, fault has been detected, and we are done. But for this one we had to go for stage number 4. Why we had to go for stage number 4? Because the fault is detected by this gate and not by this output. So, we had to go for stage number 4. But had it been a compiled code simulation, then we are not going in a stepwise manner. We are simulating the circuit totally, and then we are comparing this one with this one. So, unnecessarily many times we will be going for, here also we will go for all circuits you have to go to the exhaustive level. So, here also you would have gone for unnecessarily T4, which is not required. So, for big circuit examples we can verify that always you will be at lot of gains if you are going for a compiled code simulation. Sorry, you are going for a event driven simulation. So, this was one example in case of serial fault simulation. So, now one small thing I would like to add before closing on to this lecture, that is we are always saying that this level is stuck at 0, this level is stuck at 1. Then, but algorithmically or in a circuit nature, how do you insert a fault? This is very simple. So, if you want to add a stuck at 0 fault at this net, you put a AND gate with, this is the normal, this input was normally I2, you put a AND gate with 1 bit 0. So, always it will be 0. So, this mimics a stuck at 0 fault. If you want a stuck at 1 fault over here, then this is your OG2, and you put a OR gate with 1 input fixed at 1. So, this will mimic your stuck at 1 fault, and this is going to mimic your stuck at 0. So, this is how you can mimic. Okay, so, this was very simple, but why do we require this? Because when you are using a fault simulator, then you cannot say this is stuck at 0, this is stuck at 1, because writing it as stuck at 0 and stuck at 1 will not be handled by a circuit simulator. So, what it will do? You have to represent stuck at 0 and stuck at 1 by means of some gates, and there will be mimicry is required, and this mimicry will let you fault simulation for this part of the circuit. So, with this we stop today, and so what we have is remaining for the next 2 series of lectures in this fault simulation. So, here we have improved on fault simulation by we are not using compiled code. So, we have the better technique called event driven simulation, but still our faults were serial. So, we took fault 1, fault 2, fault 3 and so on for a given random band. That is not good. Then tomorrow or in the next lecture, what you are going to see is that how can you apply a pattern P1 and see in parallel, can you check whether fault 1, fault 2, fault 3 and fault 4 are detectable in one go by this test pattern. So, that we are going to see in the next class, and several other similar algorithms which can enhance the performance of your fault simulation algorithms. Thank you.